Looks like people are still joining. Let's wait one more minute. In the meantime, hope you can see my screen and hear me clearly. If not, please let me know on chat. Good evening. Hope you can hear me clearly. Great. Okay, let's get started. Okay, welcome to the week 7 live session of the CS104 course. So, we'll start off, we'll skip this since I think most of you have attended this and are familiar with it. And let's move to the questions that were asked last week. So first thing was, what is momentum, right? Again, I've not given too much of an explanation here because you don't need to know the details of this for the perspective of this course. But I've attached a resource here, and Papers with Code is generally a good website which kind of summarizes good ML research papers, right? So you will find, for instance, if you want to learn about a model and you want to maybe compare that model with its previous one, right? Papers with Code is a good website. Let me just. So, for instance, you'll find a lot of details about a model and about various implementations of it, and then you'll find a lot of useful resources and data sets and things like that here. So I've given you this link to Momentum, so you can also go look at it. And here is a GIF that kind of also gives you a very nice summary. So the purple is your stochastic gradient descent with momentum, and the blue is the one without momentum, right? So in ML and convergence broadly, many times you will hear about this global minimum versus local minimum, right? So what you see on the right is a local minima. Why is it a local minima? You can see that the curve kind of flattens out there and it looks like an optimum, but as you can see here, there is something near it that is a global minima, right? Overall, this is the minima and this is where your algorithm has to converge at. So this is what SGD tries to do, but in some cases it can get stuck here. As you see the blue one, right? It comes here and it gets stuck here. So many times you will hear about this getting stuck in a local minima. So momentum is one of those ML techniques that is used with SGD. And why the name momentum? As you can see from this purple ball, when it reaches here, it's almost as if it gets a push. It gets that extra momentum to come and find the global minima, right? So I think this is a very good visual to help you understand how momentum is useful. But I've not gone into the details of momentum, but if you're interested, this Papers with Code is a good site. So please feel free to go look at it. Yeah, the other question I got was with the Tau transfer learning toolkit, right? What is the difference between adapt and optimize? So here are some examples, right? Adapt broadly includes things like your transfer learning, where you take the model and you kind of uh, collect data in order to retrain it, and you might also do some fine tuning or some hyperparameter tuning. For instance, what batch size do I use, what optimizer do I use, things like that. These all come into the adapt phase. Now optimize is things like your pruning of the model, quantization, and some hardware specific optimizations. Let's say you're trying to run it on a particular GPU and you try to do some optimizations which address that. And similarly, it could also be benchmarking. So it could be a lot of these things. Okay, looks like people are still joining, and that's okay, we'll keep going. So this is broadly the difference between adapt and optimize. But I think overall what you need to know, this is just terminology, right? Broadly what you need to keep in mind is the transfer learning workflow together. So I think another question I got was on summarizing this video 4, right? So what I would recommend, video 4 was actually a very hands-on demo of this workflow. So we took a pre-trained model and then we trained it with some new data and then we evaluated it, right? And then we pruned it further and then we retrained it, and then we evaluated it. So this was kind of the high level overview of what is done. But since I also don't have access to the notebook, I will not be able to give you a code level walkthrough. So instead, what I would recommend is, when you watch the video, pay attention to the comments in the notebook. And so basically you would see something like step 1, step 2, step 3, right? So those have a title and they have like a summary of what that step is. So pay attention to those comments in the notebook and pause the video wherever you need to. Watch it at 0.5x also if you need to. Mute it, and kind of, if the audio distracts you, mute it and play it without audio, and pay attention to the comments. So you will, and keep this diagram in mind, keep it open side by side. Then you will kind of be able to relate the steps that you see in the notebook with the steps that are outlined in this workflow. And I think somebody had asked about getting access to the notebooks, but I'm just checking the Google group. I don't see anything there. So in case you haven't gotten access to that yet, please ask, because getting access to the notebook will really help you understand this better. I think you guys already noticed that last week, so please feel free to ask. Share what? Notebooks. I don't have access to the notebooks myself. I think the course instructor and the regular TAs of the course will have access. So the only way for you to communicate to them is on this Google group. So please do that, and they should be able to share the notebooks with you. You did not reach out. Oh, please do that on the Google group, because I think that's the only way to get access to the notebooks. And I'll also see if I can get them to share that. Okay, so let's move to the next thing. So again, one of you had asked about environment variables, right? So like the name suggests, again, this is a good beginner level resource to understand what environment variables are. And if you have installed various utilities, a very common example, this is why I picked this, right? A very common example that you would see is Google Drive link for what? So there is a Google group that you can get access to by going to the course page and then saying ask a question. But let me see if I can share the link with you directly. Yeah, so if you're not aware of this, this is where questions are asked about various things, and you will get replies from the official instructor and whoever is managing this for the course. So please ask there. Yeah, so let's move on. So again, if you've installed a utility, you would have sometimes seen the utility asking you to add that path to this environment variable, right, called path. That's a very common example. Similarly, you might have seen home. So there are ways where you can set these variables, where you can view them, modify them. So this will take you through some examples like that, right? For instance, you can write a simple bash script to just echo this variable name, and you can also append something to it and then see what happens. Again, do this with care, because you don't want to change some behavior that you have. And they are actually used for doing a lot of sophisticated things also, right? For instance, path is a very common use case. If you try to launch a utility, let's say launch Python, right? Your system path is where it first searches for the Python utility, for the exe executable file, right? But these environment variables may be used for a lot of sophisticated things. For instance, one environment variable which I'm not sure if you guys would have heard or used, but there is something called LD underscore preload. So this is used very frequently by profilers to do some code injection. Basically, let's say you have a piece of code, right? Let's say this is a system call or something like that, and you want to now get the time spent in the system call. So let's say the profiler adds some statements before and after the system call. This is called code injection. So how it does this is, once you set this LD preload to some value that the tool tells you to set, it will automatically replace all the system calls by its version of system calls, right? So this is again one very sophisticated use of an environment variable, but this is in general, and in Linux you have to be careful about what environment you're trying to run something in, because sometimes these variables may not be set or they may not be passed. For instance, when you run something with sudo versus when you run something without sudo, you will see a lot of issues coming up saying, oh, this utility is not found or this variable is not set, right? So that's something good that the that you should, that kind of tells you the importance of these environment variables and how to set them, how to pass them to environments, etc. Data formats was another thing asked last week. I didn't get the time to make content on this because this is not part of your course where I can just pick it up and put it. But this I will definitely cover next week because it's an important thing to know in general, right? So we'll start with the IEEE 754 format, look at FP16, FP32, and then we'll spend some time understanding bfloat 16. So that will cover the data format side of things. How can I open Jupyter Notebook in Ubuntu? Okay, this is again a hands-on thing. Let me see if I can pull up something for you right now. So were you able to install Jupyter on Ubuntu? I think last time you had asked and I had shared some link that would help you do that. Did that work? Okay, you are able to install. Good. So next I think was to launch the Jupyter notebook by just saying Jupyter space notebook, and that was supposed to open a tab in the browser, right? You basically just have to use the command Jupyter space notebook. Did that work? Yeah, this is all you are supposed to run in your terminal, and then this will open up a new tab in your web browser. That's all it's supposed to take. So it's very easy. If you run into issues with this, then let me know the exact error that you're facing, because otherwise I cannot kind of figure out what's going wrong. But installation seems straightforward. There's nothing more to it than that. Yeah, that's pretty much it. I looked at 2 or 3 tutorials. Here is one more. Yeah, that's all there is to it. There is no hyphen, it's space notebook. Do you still get the same error when you try with a space? Okay, let me then look at that. But maybe we'll discuss this after the break so that I get a little bit of time to look up the error. So looks like it's installed from what you're getting. So it's just a matter of the syntax that you give it. Uh, yeah, the command itself could have changed is also what I'm getting from another site. Try a Python 3-m notebook. I see. I wonder if it got. Okay, let me try this out in the break and then see if I'm able to figure it out. I'm sure it'll work for you. So I will let you know. Okay, before we move to the recap, okay, Project Jupyter. Yeah, the command might have changed. I'm not sure. I haven't used notebooks in a while, and this used to work, but I'm not sure if it has changed now. So you might need to find what is the command that works right now. And if any of you other folks have tried this out and know how to get it working, feel free to post on chat, right? Uh, that will make it easier. Yeah. In the meantime, are there any other doubts in the week 7's course content? Okay, so yeah, sounds good. The installation part is fine. That should have taken care of installing it, and seems like you have it installed because you're able to see all the options for the command and things like that. So maybe the Jupyter notebook command is no longer valid. So we can check that. I'll check it out in the break and then let you know if I'm able to find something quickly. In general, a good tip is to search on Stack Overflow. You will usually find people who've asked very similar questions or the same thing even, and you can try out some of those things. That should help you. But I'll see if I can figure this out in 5 minutes. Anyway, before we move to the recap, any other doubts from week so far, right? Week 1 to week 6 or even week 7? I'll give you a minute. Think about any doubts or questions you have and then let me know. Yeah, I got that. That was the simplest tutorial I could also find, and that's why I shared it. But yeah, let's see. Okay, if no other questions, let's move on to the recap part of the session. Okay, so we start off here with distributed no errors. Yeah, that's good. That looks like your installation went fine. So that sounds fine to me. There's nothing of concern with the installation itself, unless the installation steps have also changed, which might be possible, right? So I'll take a look at it during the break. Okay, so why do we need distributed deep learning? I think we touched upon this in a previous session as well, right? So you can see here, this is reflective of, this is a 2015 Microsoft ResNet, and you can see that it has 60 million parameters. And then 2016, there is Deep Speech 2, which has 300 million parameters. 2017 has 8,700, and obviously there is a lot more data from 2023 with the LLMs and all that's happening today, right? So you can see both the compute of the model. Okay, after that, is there something missing or the command has changed? Yeah, I'm not sure. Like I said, I have not used Jupyter notebooks in a while, so I'll try to do this, replicate this, and see, since it's simple enough, I'll try to replicate this and get back to you in 5 minutes if I'm able to. If not, again, ask this in the Google group. Maybe somebody will share a different document which will help you figure it out. And okay, next question, are these sufficient to pass the exam? So these are kind of indicative of the questions that you may be asked. The exact same questions may not be asked, but if you're able to do well in the problems discussed in these live sessions, as well as the ones that are discussed as well as the ones that you're given for your assignments, that means that you have a good shot at doing the exam well. That's all I can say. It'll be very similar. It might not be the same. That's all. Hope that answers your question. Great. Any other questions or doubts or things on the exam? I know you have 5 weeks left. MCQ questions, yes, unless you're explicitly told otherwise. I think most NPTEL exams have purely MCQs. This one will be the same too. Any other doubts or questions? Okay, if not, let's move on. So like I was saying, right, you see that, so this is, whenever you think of deep learning, there are three things that come into play, right? Compute, data, and the algorithms. So you can see the compute requirement of the models that is going on increasing. Similarly, the data sets also in size and the number of samples keep on increasing, and then you have your algorithms, right? Revise week 6 assignment questions. Let me see, when was the deadline for that? Is that already done? If it is done, we can definitely discuss it, but if the deadline is still ongoing, then policy is that we can't discuss current assignments. Yeah, it looks like the deadline is already done, so I'll make a note of that. We can definitely discuss it next class. All questions in week 6 or any particular questions? Questions are different. Okay. Okay, we can go through the whole thing. It's just it's just very similar questions, right? So we can definitely discuss them. And I see that sometimes, right, there might be questions that kind of are from a different week. For instance, I see a question here with no, I don't think so. Yeah, most of the questions do look like they're from week 6 itself. So yeah, we can definitely discuss them. It should be fine. Let's see, if we have time today, then we'll discuss them today itself. If not, we will do them in the next class. Okay, So yeah, so that's kind of why we do distributed deep learning, right? Basically, as your models increase, model sizes increase, basically this number of parameters that you see, this directly contributes to the memory that the model will occupy. And once this memory increases, it beyond a certain point, it cannot fit into the GPU memory, a single GPU, right? So that's when one of the reasons where you try to do a distributed deep learning. The other thing, because of the data increase, is that you might have a lot of data to train on, and even though a model fits on a single GPU, you might want to replicate it on multiple machines so that you can partition this data and then train, right? This is another reason for distributed training. These are the just motivating examples, and they directly also give you an idea of why data parallelism, why model parallelism. Revise what exactly? Yeah, so this again talks about this scaling in terms of your compute, data set, and in terms of the parameters. So the loss keeps coming down, right? You can see with an increase in parameters, with an increase in data set, with an increase in compute. So that's kind of what we spoke about here also. So that motivates the need for distributed training. First page of what exactly? This is it. Okay, yeah, so I was saying that so broadly you see the trend both here and here, right? That the compute of models keeps growing. So this flops, I think we spoke about it earlier also, floating point operations per second, right? Or just if you talk about number of floating point operations, that keeps increasing over time. What this indicates is the number of, broadly it indicates the compute that you have to do for a model. So if you're not familiar with this, a good idea is to, let's take one matrix multiplication, right? Let's say we are doing A cross B, and assuming that these are both in the floating point format, this is called one floating point operation. Now this gives me a good way to compare different models. So let's say I have a model which involves 10 of these, right? So then I'll say 10 floating point operations is the compute that this model takes. Similarly, I can have another that takes 100, right? So then I'll say that model's compute is 100 flops. So this gives you a reference or a baseline against which you can compare the compute of different models. So this tells you how the compute of deep learning itself is growing. So as you see these numbers increase, it means that these have more and more operations, right? And that in turn motivates the need for speeding it up, for distributing the workload across multiple machines and then speeding it up. Hope that helps. Okay, so now that we've seen, great. Now that we've seen why we need to do distributed training, what are the benefits that you can get? Again, like we spoke about, larger models is the first thing, and this, keep in mind that this is in the same duration of time. You can train on more data, you can train more iterations. For instance, let's think of data parallelism, right? Let's say one GPU was able to train on 100 samples in 1 minute. Now my data set size doubles. I have 200 samples. So what I do is I give another GPU the same 100 samples, and this will also take 1 minute, and I might synchronize after this, or I might even give 50-50 and then again 50-50. But notice that the work has doubled here. I'm now doing 200 samples or 200 images, which is more data in the same time, right? So this is that. And similarly, you can also say I'm able to do more iterations because I finish the data that I have faster, and then I'm able to do more iterations. And similarly, if a model doesn't fit in GPU memory and now I kind of distributed it across multiple GPUs, I'll be able to accommodate a larger model. So broadly, it can either get you better results or it can help get the same results faster. These are two ways to look at it. So here are some examples which will help you understand this. So ResNet 50, 90 epochs training. Again, as a recap, an epoch is where you finish training on the entire dataset once. And remember that training is kind of iterative, so it happens over multiple epochs. In single GPU can be work in more than one machine parallelly. I don't understand. So you can have a scenario where you have one machine or one system that has multiple GPUs. So this is like a single machine multiple GPU where yes, you can do things parallelly, but and similarly you can have two different machines which each have one GPU, and here also you can do things parallelly. So those are the two scenarios. Hopefully what you asked is one of these. If not, you can correct me. Single GPU, multiple machine. Yeah, which is basically this, right? This is what you're talking about. Or is it something else? Okay, great. Yeah, you can do things like this. Both are valid. You can have one system with multiple GPUs, or you can have multiple with one GPU each. Both are possible. So here's a concrete example. If you use one A100 GPU, it takes 14 hours. If you use 8, it takes 3 hours. Now notice something interesting here. One is taking 14 hours. By your knowledge of linear equations, how much should 8 take? Any guesses? Okay, if that seems too difficult, one GPU it takes 14 hours. If I use two GPUs, how much do you think it will take? It will reduce definitely, but is there a number that comes to your mind? Seven hours. Yes, that's the obvious guess, right? That's what you'd think. That you're basically doubling your compute and now you're reducing time to half. And similarly, for an 8x increase in compute, you would expect the time to come down by an 8x factor, right? So it's interesting that you notice here that it stays at 3 hours. And this is something again that was not maybe pointed out in the slides, but as you go through some of these paradigms, you will understand a little more on why could that happen. For instance, there is a lot of communication involved. There are things about asynchronous training and synchronous training, that many of those things could cause something like this. So this is just something to keep in mind broadly, but it still reduces the time, so using more GPUs is beneficial. Okay, is there a command to work on one GPU? Not really. I mean, the default setting is one GPU. So if you're using PyTorch, I think there is a way. So you can. There's a way to select the device, right? I think it was there in one of the earlier weeks. I don't remember which week, but there's a way where you can set the device to either a CPU or a GPU, and before that you check if using this command called, I think, is CUDA available. You check if the GPU is kind of available and visible to torch, meaning that all your CUDA and other libraries are properly installed. After that, you go ahead and allocate the device to either CPU or GPU. That's all you need to do. It's one line, right? After that, everything will work by default, whatever code you write on PyTorch. The tricky part is writing distributed code, for which in PyTorch you have distributed data parallel, a lot of things that we have looked at in the previous classes. So writing code for a single GPU is very easy. It's all the default settings. Okay, great. So any questions so far before we continue? Okay, let's go ahead and continue then. So like I was talking about before, we have two ways of spreading or distributing the training workload across GPUs. So one is you could take the input data and spread it across all GPUs. This is called data parallelism. It's a very obvious way, right? You can increase training throughput. And again, we spoke about some of the details of this, things like batch size, right? So yeah, I think that's also fairly clear by now. The other thing you can do is to spread the model computation across GPUs. This is called model parallelism. So this is slightly more difficult, and you can do it in various ways. For instance, a very commonly spoken about way is this different layers on different GPUs. So let's say I have a model with 4 layers. I simply say that layer 1 and layer 2 will run on GPU 1 and 3 and 4 will run on GPU 4. So I basically need to pass in the forward pass, I need to pass activations between these two layers which are on a different GPU or a different machine's GPU, right? The other thing I could do is also take a single layer and partition it across GPUs. For instance, if this is one layer, I can spread this layer itself into two GPUs. So that's also another way to do model parallelism. Does it really take half time if we work on two GPUs? No, that's the expectation. Reality can be different. So some things that you have to think about are what are these extra things that basically add up to your ideal time, right? Because if you think about something simple like data parallelism where both your GPUs are doing the same work, then you expect half the time, right? So if you're not getting half the time, then you should look at what problems there are. Maybe it's communication, maybe it's something else, right? But in reality, it may not be half. Half is again an ideal thing, but it also gives you an upper bound for how much speed up to expect. Reduces a little bit, yes, in practice you might see a lot of those effects kicking in. Okay, so we already spoke about this is just a pictorial representation. So this is where the model is replicated across all workers. This is data parallelism, and you can see here that the layers, assuming these white boxes are layers, are partitioned across different workers, and that's model parallelism. So I think this is clear, but any questions before we move ahead? In the lecture it was said that it's not necessary to take half, it may be reduced or it may not be. Yeah, so that's the reality of some of these things, right? For instance, if you do something where communication, we'll see later on in the lecture, where depending on the links that you have between GPUs, right? In the lecture it was discussed that you might have NVLink, you might have PCIe, and it might go through the CPU, it might not go through the CPU. So that's one of the examples where you add a lot of communication overhead, as a result of which your time may reduce very little, or in a very bad scenario it might not even reduce. The other thing is if you did something that interfered with the convergence itself, with the accuracy. For instance, asynchronous training is one of the classic examples of that. Then it might change the number of iterations it takes to get a target accuracy. So many times in training, so this example here, for instance, said that they are comparing 90 epochs, but there might be some cases where they are saying time to accuracy, right? TTA. This is also a very commonly used metric in deep learning. This means how much time does it take for my model to reach some accuracy. Let's say that accuracy is 95%. Now, if I did something that changed the convergence behavior of the model, I may have to run more iterations. So instead of 100 iterations, I might have to do 150 iterations to reach the same accuracy target in a distributed setting. So as a result of this, even though you have more hardware resources available, you're essentially doing more work to get to the same point, right? And again, because of this, you might not see a reduction in time. You might see a slight reduction. Sometimes, as it was said in the lecture, you might even see an increase in time. So all of these things are possible. Okay, hope that clarifies things. But let's get to the communication side of things, talk a little bit about those, and then we will see. Okay, model versus data parallelism. Data parallel, again, I think is TTA stands for time to accuracy, right? So one metric I can use is time to train a certain number of epochs, like this 90 epochs. The other metric I can use is, because ML practitioners care a lot about accuracy. So they say, I don't care if you train, because think of this, if you affected the accuracy, and if I told you that after 14 hours I'm able to give you 98%, and after 3 hours I'm able to give you 60%, right? As an ML practitioner, they would probably pick this option, right? Because even though you're saying you're running things faster here, you're not getting to the same level of accuracy. So this metric in that sense is not a very complete or useful one in terms of ML, given that you're using something that changes the accuracy or the convergence behavior. So many times what is used is time to accuracy, where you're saying, I want this accuracy from my model. Now give me the time it takes to get there. And that's another way of comparing two different settings. Maybe running on one single GPU versus running on 10, right? That's what I was talking about. There are different metrics that you can use. So whenever you look at a method, right, whether it's data parallelism or model parallelism or some other very different kind of distribution technique that you hear about, ask yourself if it is semantically or in the fundamental thing that it tries to do, does it change the accuracy side of things, or does it just make things faster without actually touching the convergence behavior? Because this convergence behavior is very tricky in the whole deep learning field, right? Many times, like in the very first example we saw, things like getting stuck in the local minima or having a lot of oscillations and noise before reaching a minimum is very possible depending on what methods you use. Hello, am I audible? I think I had a little bit of a network issue. Hopefully I'm back. Yeah, okay, let's see what the comment is. If we provide less data and got good accuracy, and we add more data, then accuracy would be, that's fair. But what we do when we compare things like this is we keep the data set the same. We don't change the data set and compare, because that's not a fair way of comparing, right? Because your train and test data set will decide the time it takes to train and the accuracy that you get. So what is usually done is you retain the same data set, and then you put out such metrics, unless you're doing something like transfer learning. There the time for that you take for this incremental retraining is not compared to the time that it takes to train the original model. Those are two different things. In the distributed setting, typically we compare how long does it take to run on a single machine or a single GPU versus how long it takes after you've applied some distribution strategy. And in that case, we don't change the data set. Even if the data set is split across multiple machines, overall we are looking at the time it takes to train on the same data set, the full data set. Hope that clarifies things. Any other questions before we move forward? In data parallelism, we provide a single input. I am not sure about what you mean by a single input. So, for instance, let's say, I think we worked out this a little earlier. Let's say your batch size is 16, right? This means that you would be feeding, this is again in a single GPU case. This means that you would be passing these 16 images to the network at the same time. Now, if I were to do this in a distributed setting, I might change this batch size or I might keep it the same. That's a different question. But what I would do, and let's say we had 4 of these batches together which make up the data set. So, the total number of data samples is 64. Now, one thing I can do is to, let's say I have 4 GPUs here. I can give 16 inputs to this, 16 to this, 16 to this and 16 to this. This is one simple example for data parallelism. But I can also give something like, I can change this number, right? It doesn't have to be same as the original batch size. But what you should try and understand is what does a batch mean in terms of synchronizing the gradients, and when is that equivalence achieved when you try to do something like this. So here essentially, I think I asked this in a previous live session. So essentially here what happens, because you are synchronizing after all these 4 GPUs finish computations, your effective batch size is 64. So it's not really about single input, right? If your batch size equal to 1, then yeah, at any given point your GPU is processing one image, and all your GPUs that are part of this data parallelism setup work on that same one image. But typically in training we do use batch sizes to exploit the parallelism of the GPU. So basically when you give this batch size equal to 16 or any other number greater than 1, remember that the GPU has all of these CUDA cores or these SMs, right? They will kind of process this full batch of images in parallel, and that gives you a better utilization of your GPU, and overall it reduces the training time also. So that's how it is. Hope this helps. Any other questions? Data in a single input. Again, if your input refers to a batch, sure. And in a different GPU, yes. So if you're asking about where would the data be stored, right? So if these are all different GPUs, for instance, one scenario could be that the data sits on some networked storage that you can access from each of these GPUs. Or another simple thing you can do is to partition the data and then shard it, what is typically called sharding, right? And you can partition that and put it onto that machine's storage. So then the typical pipeline that is followed, which is your disk or your IO to CPU memory and then to GPU memory, the same thing would be followed. Data in a single input and in a different GPU, will it work? I don't understand what you mean by single input. Maybe try and rephrase your question and I'll try to answer it. Okay, let's keep going because we're almost at 8 o'clock. Model parallelism, again we spoke about, allows using a bigger model. All workers train on the same data and parts of the model are distributed across GPUs. And then you pass, if you split it layer wise, you will have to pass activations between GPUs. This is a little bit harder to implement as compared to data parallelism. So here's again another pictorial representation. So here in data parallelism you do averaging of gradients. Here instead you're kind of exchanging activations between this GPU1 and GPU2. Yeah, I think this must be clear. So maybe your doubt will get answered after we understand what is synchronous and asynchronous. So here, um, so for instance, this one is a parameter server where it's a dedicated server. Variables are created on these parameter servers, and your workers, here you have two workers, they read the variables from this server, and then each of these workers proceeds to update its copy of variables. There is no synchronization between the variables. At some point, they will send data back to the server, and then the server will update its global copy, right? So this is why it's called asynchronous. Basically, there is no synchronization between these two, and because of that there is no waiting also. So here, for instance, if worker 1 and worker 2 are not identical, what would happen is, let's say worker 1 finished training on its whatever it was supposed to train on, and now it needs to wait for worker 2 to finish and then send it all these variables, right? Because it has to synchronize before going to the next mini batch. That's the idea. So here, on the other hand, you don't have that need for synchronizing things, and that's why this is called asynchronous. So this is an important difference to understand. So ask yourself this: although here we have a parameter server and the example that's given to you is asynchronous, think about whether you can have synchronous with a parameter server, right? It's important that you kind of make this distinction between a policy and a mechanism. So here, the parameter server is how you implement asynchrony. The policy is kind of asynchrony, and the mechanism that you use for it is a parameter server. But can I do this using a parameter server? If you think about it, you'll realize that you can, and it is one of the ways that is used to do synchronous training as well. So what you need to understand is this difference between synchronous and asynchronous. And you will see that earlier I was talking about accuracy and convergence behavior, right? Whenever you do asynchronous, because essentially what happens here is that this continuous training on its data without synchronizing with the other, and this also does the same. They only periodically talk through this server, right? So as a result of that, there are some effects. Logically, you can think of this as two diverging things merging at some point, right? As a result of this, the convergence behavior changes because you're no longer doing what you do as part of normal stochastic gradient descent. There has been a lot of work that has shown that in some settings synchronous asynchronous works very well and things like that, but always remember that this changes the behavior of the algorithm itself, and therefore its implications may not be straightforward, right? Like I said, it might increase the number of epochs it takes to get to a certain accuracy. So you might have issues like that with asynchronous. With synchronous, you don't have any of that because you're still maintaining whatever SGD needs, right? You're synchronizing with the workers, and basically only then do they proceed to do their computation. So hopefully this explains, this is an important difference to understand. Hopefully this is clear. Any doubts on this? Clear. Great. Okay, so let's see what we have. So we'll move to the network side of things, but maybe this is a good time to take a break. I think we had a lot of concepts. So it's 8:02. We'll resume at 8:07, and I'll keep the call running, but we'll feel free to take a break and come back. Okay, let's continue. So, on the Jupyter side of things, what I tried out is a simpler variant that seemed to work. So, it's simply pip install notebook followed by Jupyter notebook. But since you've tried out the other method, you might, if you run into some dependency issues or some errors with this, you might need to first uninstall and then try this method. But this is the officially recommended one on the Jupyter website, so I would suggest sticking to this, right? With third party websites, sometimes instructions seem to be clear, but then you don't know when the website was updated, whereas the tool's official website typically would have updated it according to the latest release. So please try this one out after class today, and like I said, if you face issues, please uninstall the existing one that you have and then try this out. Hopefully that'll help sort it out. Okay, let's move on. So is that clear to as to what you need to? Oh, not the full instructions of it. So you can go to the, I'll tell you. I'll give you the exact commands so that you. Yeah, just this much. This worked for me on an Ubuntu VM, so it should work for you. The rest you can ignore. So there are different variants of it and different things for Mac OS and things like that. You can ignore all of that. Okay, so let's continue with the recap. So when it comes to system topology, no, just pip install notebook. The two commands that I've pasted just above, you can just paste them and try running them. Yeah. So we spoke about latency versus throughput the previous day in one of the previous sessions in a lot of detail. So I'm not going to go into too much detail here, but for anyone who missed that session, please go back and look at it. I think it was 2 weeks ago. So we had this very nice example of a bus and a car, right? And looking at them in terms of how many people, it's working. Great, happy to hear that. Yeah, sorry it took you so long, but yeah, you learn something by trying out these things, right? For instance, one thing you've learned is not to look at a third party website for instructions on all of this and then look at the main page. So, yeah. Okay, so as I was saying, there was this example of a bus and a car, and we compared them in terms of how long does it take to transport a set of people and how many people can it transport at the same time, right? So one of these is throughput, the other is latency. So here also you can look at this. So these are the official definitions. Time taken for the transfer of a single packet of data, that's latency. Quantity of data that can be transferred in the unit of time. You will again, throughput is one way of throughput is a very common terminology that's used for this. So if you look at transferring data across an interconnect, then you can define throughput as bus width divided by latency. But again, if you are not clear on what latency and throughput is, please go and refer to that example that I've put in one of the live sessions. It will really help you understand it with a very simple example. So what is the message that you get from here? Revise. I think today we'll kind of run out of time because we're already at 8:10. So what you can go is go look in Google Drive on just search the same drive link that I share every time, right? Maybe I'll paste that in chat again if you've not seen it. sharing my screen is very complicated because I have screen recording going on to put on YouTube. So it is set to a window, it will only capture Google Meet, and I don't want to mess with it because in case I do, then the recording might not be proper. So you can go to this drive link and then just search for throughput and latency, and it will show up, right? And you can look for that particular live sessions video and scroll to that slide number quickly. So that will give you that example. If you still don't understand it after watching it, then let me know and we can talk about it the next time. But otherwise I think we'll run out of time, so we'll not go through that again. But it's important to understand that because now you see some real world implications of that, right? For instance, how wide your bus is directly decides your throughput, and how long it takes to send a single packet of data is latency, and you will see how different communication links and different topologies affect both latency and throughput. And this matters because now once you go into distributed training, you are going to be exchanging data on the network, right? So your system topology, your interconnects, all of these decide your latency and throughput and therefore your training time. So again, a quick revision of this. So we saw things like GPU direct, and so even here there is a version with a peer-to-peer transfer, and there is a version with support for RDMA as well. So RDMA is basically where you can remotely access this memory, and here what you see with GPU direct is that there is no CPU involvement. The GPU can directly kind of talk to each other, and this is on a remote machine, right? Again, all of these are old concepts, so please feel free to go look at that particular lecture. And again, we spoke about having different links, right? For instance, there is something called an NV link which connects GPUs directly. If not, so you have a PCIe switch which connects the GPU to the CPU. So typically communication will go through this PCIe switch to the CPU and then to the other GPU. But NVLink is a direct GPU to GPU communication. So peer-to-peer over NVLink looks like this. It just goes like this. P2P over PCIe looks like this, right? And here you can notice that there is no CPU involvement. So those are all the different ways. So you see basically how some of these things can affect your data transfer time. And just the way we looked at NVIDIA SMI in an earlier lecture, when it comes to topology and the kind of links that you have, this topo-m is a good tool to use. And again, this would be useful only when you have one single system with multiple GPUs, right? If not, you won't be able to see all this information. So notice that it is run on DJX1. If you run this on a normal system, right, you might see one line or something like that, because it's basically how that particular GPU is connected to the CPU. That's all you will see. So here you notice different terminologies. You see NV1, and this table below will tell you what are these these different things stand for, right? So I think from the lecture you would have already known that this 1 or 2 means how many NV links there are, and similarly you have sys, you have PICs, you have different things, right? This means that it traverses a single PCIe bridge. This means that it traverses multiple PCIe bridges, and sys means it traverses PCIe as well as the SMP interconnect. So you'll see that there is a lot of variation. So even though you think of a DGX as a very simple thing with 2 CPUs and 8 GPUs, notice the complexity when it comes to this system topology. And as we will kind of realize, this system topology has an effect on training time once you get into the distributed space. So you have to be clever and efficient about which GPUs you use for what, how you exchange data and things like that. So notice that there are NV links available. There's also a PCIe path available. That's what this diagram shows you. And yeah, so if you just use data parallelism with PCIe, you're basically going to load data and do the gradient averaging. Both will share the same communication resources because both of them happen through PCIe, right? So it might result in congestion depending on how much bandwidth you need. And given that the GPU is so much faster, typically you will hit congestion when you try to do something like this. So what is something better that you could do? You could use NVLink for this, let's say, gradient averaging, and you could use data loading over PCIe. So essentially now this gives you additional channels, right? So it's like, think of having one road and think of having another road that is kind of longer, right? Both take you to the destination. Now if you have just one vehicle, you have to make the choice of which road to take, right? This is your choice 1, this is your choice 2. But if you have multiple vehicles, then you can do something smart like sending one through this and the other through this. That way there is no congestion and you kind of increase your throughput, right? So that's what is done here. For different things you use different paths. And why would data loading and gradient averaging happen at the same time? If you think about that, there are different stages, right? And there are different optimizations. For instance, you might prefetch the data, and this is something we learned again in 2 or 3 lectures before. So while the gradient averaging is happening itself, you might prefetch the data for the next mini batch. Why you want to do this is basically once the gradient averaging finishes, the GPU can immediately start working, right? So both of these can be happening at the same time. If they are not happening at the same time, you won't hit this congestion. But given that they can be happening at the same time, this is a valid concern. Please explain that line. So did you mean this analogy about traffic and data loading and gradient averaging? Okay. So data loading is basically, let's talk about images again, right? Let's say you have 16 images. Now again we have this storage, which is your IO device, right? It can be a hard disk, it can be an SSD, it can be any sort of IO, and from there you have to kind of get this data into memory. This is typically CPU memory, and then finally there is a copy into GPU memory, right? So each time you process a mini batch, you need to do this. But what can happen is, what as an optimization, what you can do, so you can think of the computation as forward pass, backward pass, and then your weight update, right? Basically this gradient averaging and weight update. Let's just say weight update here. So what I need typically, if I didn't do any optimizations, this is how it looks like. So first I load the data, then I do the forward pass, which is basically going along the direction of the layers, right? Then I do the back propagation, I compute all the gradients, and in a distributed setting you need to exchange the gradients and average them basically, right? And then you do the weight update. So what I can do as an optimization is have the data loading happen in parallel. So I might start it somewhere here itself, and this is for the next batch, right? Not the same batch. So this batch has to be loaded by this point, only then the forward pass can start. But now to avoid this delay for the next batch, what I can do for the data loading is to make it happen in parallel. So because of that, the gradient averaging, which happens here, somewhere here, might happen in parallel with the data loading of the next batch. So since both of them use the same path, the PCI path, there might be congestion. So that's the reason we talk about using NVLink for one and PCI for the other. Is that clear now? data loading without using ETL, it could be using it also, depending on again what frameworks you use and what APIs you use. You can still have something like a prefetch or pre-process optimization happening in parallel with this. So this is a conceptual thing. How you implement it depends. Okay, let's move on to the next part. So yeah, this is a library. So again, if you've been seeing this pattern, right, it's a very common thing in tools and frameworks. You basically talk about how something is very difficult to do, and you show that there is a promise for optimizing something, and then you come up with a tool that automatically does this, right? So NCCL is one of those. It's called NVIDIA. It stands for NVIDIA Collective Communications Library. So it is used in a multi-GPU and multi-node setting. So again, it can do a lot of things, but broadly it is intended to be a high performance communication library. So it can kind of automatically do this topology detection that we spoke about. It can understand how GPUs are connected with each other, and therefore it will make sure that your distributed training maximizes inter GPU bandwidth utilization. So it will make sure to smartly distribute the workload so that we won't encounter some of these congestion bottlenecks. Basically, it's topology aware communication. And again, the next point, as you could predict, it's that it's easy to integrate, and MPI is one of the standard communication libraries. So it's MPI compatible, and it helps scale HPC and deep learning applications over PCIe and NVLink, and supports a bunch of frameworks such as Caffe, Microsoft Cognitive Toolkit, MXNet, PyTorch, etc. What is topology? So this in this context, right? This, we are talking about a communication topology here. So broadly, it is about how these GPUs are connected to each other. Is it through an NVLink? Is it through PCIe? Is it through multiple NVLinks, etc.? Minimize use of PCIe switch. So in a system where you have both NVLink and PCIe, definitely that's the first thing that I would expect it to do. Let's say you only had PCIe links, then also it might try to, for instance here, right, you saw this one standing for traversing a single PCIe bridge, traversing multiple PCI bridges. So again, this might cause a little more delay. So it might pick even the PCI path that it picks, it might pick it smartly if there are multiple available. So it will basically use all the topology information that it gets from a system. It can be a system using purely NVLink, purely PCIe, or a combination of the two, and then accordingly it would decide what to do. Does that help? Okay, with that we move on from the network part of it to the TensorFlow distribute API, right? So distribute.strategy helps you distribute training across multiple GPUs. I think we briefly saw this. So you can distribute your models and training code with minimal code changes. So broadly, again, you can summarize it into synchronous versus asynchronous. And in synchronous training, you train over different slices of input data in sync and aggregate gradients at each step. In asynchronous training, all workers are independently training over the input data and updating variables asynchronously. And again, you have in terms of hardware, you could have multiple GPUs on one machine, multiple machines, or it could even be a TPU, right? It supports all of these things. So now in this distribute itself, you have a number of options available. Let's look at a few of them. So the first one is mirrored strategy. This supports synchronous distributed training on multiple GPUs on one machine. Notice that. So it creates one replica per GPU device. Every variable is mirrored across the replicas. So these are kept in sync, obviously, because this is synchronous, right? It has to do that. Next one, multi-worker mirrored strategy. Again, this very similar to mirrored strategy. So it implements synchronous training across multiple workers, each with potentially multiple GPUs. So again, it's synchronous, so it will create copies of all variables in the model on each device across all workers. So the only difference is that it has multiple workers. That's the only thing. Next one is central storage strategy. This also does synchronous training, but instead of mirroring the variables, they are placed on the CPU and operations are replicated across all local GPUs. If there is only one GPU, then the variables are placed on that GPU. So as the name indicates, central storage, right? If there are multiple GPUs, it's placed on the CPU. If there is only one GPU, it would be on that GPU. But again, notice that this is also synchronous training, no change in that. Next comes the parameter server strategy. So this is again a common data parallel method. So it consists of multiple workers and parameter servers. Variables are created on parameter servers. Variables are not mirrored. So you don't create a copy for all of these variables, right? Instead, the GPU would do the operation and the variable will still be on the CPU. So that's the difference in the central storage strategy. Whereas in all of these mirrored and multi-workered mirror, you basically create a replica of the variable. You create a copy of it and that's there across all the GPUs. That's the difference. Okay, so parameter server. So this we already looked at and said that it can be used in asynchronous training. So it's interesting that this is not mentioned here, whether it's synchronous or asynchronous. But you can look at it in the context of TensorFlow. It probably uses it for asynchronous data parallel distributed training itself. But you can check that later. Then there is one device strategy where you place all variables and computation on a single specified device. So you can think of it as a variant of central storage, except that it gives you further flexibility on which is that single specified device. Okay. So next we will look at Horowwood very briefly. Yeah, so it's a distributed deep learning training framework, supports TensorFlow, Keras, PyTorch. Again, easy to install and use, minimal code changes, proven scalability, uses advanced algorithms from HPC. So yeah, this is broadly it, but you will notice this term scalability in a lot of deep learning libraries, for instance, will make this claim of scalability. So it's important for you to understand what is scaling in this context and what are the two variants of scaling. So we will talk about this a little, and I've given you some references also, so you can go look at that afterwards if you like it, right? But this is kind of another key concept with respect to systems, and it's useful even beyond this course, right? So it's good for you to know. So strong scaling is the first variant of scaling, and this is also referred to as Amdahl's law. So here your total problem size is fixed and the speed up you can get is limited by the sequential bottleneck. So what do I mean when I say this? Let's look at this picture on the right, that will help you understand. So this is the process that we are trying to speed up by parallelizing it or by distributing it, right? So it has two parts. This is part A, this is part B, right? Now let's say by some method I make B 5x faster. It is going to shrink from this big blue thing to this small blue thing. But notice the overall runtime. Does it change by 5x? No, right? It's the gain that you get is very small. It's definitely nowhere near 5x. In contrast, look at what happens when I make to this big portion 2x faster, and look at the overall runtime, right? So you realize that speeding up certain parts of the process give you more of a benefit than the others. Basically, the part that dominates the process should be speeded up, and that's when you get the more benefits, right? So now let's talk about this in terms of sequential and parallel, right? So if you have a given problem and the sequential part of it is say 90% or zero point 0.9, and your parallelizable part is 0.1 or 10%. Now if I take this and distribute it across 10 machines, I make it 10x faster. But what is the overall benefit that I get? That benefit is going to be limited because the overall bulk of my program is sequential. So that's what this says. Speed up is limited by the sequential bottleneck. And so here are some examples. So when you have half the process as sequential or non-optimizable and you have half as optimizable, you can still see the amount. Even if you optimize this 10x, you're basically stuck at the benefits that you get, right, because of this half. So this is the notion of strong scaling, where I keep the problem size the same and I try to speed it up by parallelizing it or by running it across different machines, right? Now we will see another variant called weak scaling, which is Gustafson's, also called Gustafson's law. So here what I do instead is I increase the problem size with the number of processors or with the number of hardware. So now again we'll take the same example. Let's say this is your serial part of the process and this is your parallel part of the work. Now when the problem size increases, so what I try to do is instead of sticking to the same problem, I increase my problem size. So, and because of that, what happens many times is that the parallel work grows, but the serial fraction of it remains the same. And because of this phenomenon, what I can now do is I can take this extra parallel work that comes with the increase in problem size and parallelize it. So you can see here that there is P into parallel work. So I can simply parallelize this part, and the serial part, as long as it remains the same, your runtime will essentially look the same, right? So the total time remains constant. So here we are talking about a speed up in strong scaling. Basically you keep the problem the same, you increase your machines. So in our example, we keep the training problem the same and we add more machines, right? Instead of one A100, you add 8 A100s and you see if you can make it faster. That's strong scaling. Now weak scaling is if I increased the problem size itself along with the number of processors, and then the overall time that it takes would remain the same. So whenever you hear claims of scaling being made, ask yourself, is it strong scaling, is it weak scaling, right? Strong scaling is more difficult to achieve than weak scaling, and this might be a little difficult to understand. It is a bit of an advanced concept, but try looking through it after this live session as well and see if you can understand. So this is a graph that shows you Amdahl's law or strong scaling, right? And you can see that this, for instance, is your 50% is parallelizable. So no matter how much you speed up your parallel portion of it, or no matter how many processors you add, even if I add 1000 or 10,000 processors, see that the speed up is limited to 2, right? This line never goes above 2. So speed up is basically if I took the speed up is a way to compare the runtime it takes after you increase the number of processors to the serial runtime, to just running it on a single machine basically. So you can see that the speed up is limited to 2, whereas if my parallelizable portion is 95%, even then, which is the stop green curve, you can see that that also saturates around 20. So even though I have 5% of serial work here, that itself causes a bottleneck, right? It's limited by this sequential bottleneck. No matter how many processors you add, notice how many processors you added here. So that's what makes strong scaling very difficult to achieve. So in contrast, weak scaling is a little easier to achieve because you increase both the processors and the data set, and that typically allows you more room to keep the runtime constant. So take a look at both of these things afterwards and see if you can understand them. Okay, so with that we are done with the recap. Any other questions before we move forward? Initial point was minimal code changes. This part, right? Horrorwood. So again, that I think I would need a Horrorwood example to show that to you. Let's see what was in your course lectures. Right. So I think you can go through the last couple of slides, right? For instance, there is an initialize Horrorwood, and then there is spinning a GPU to a single process, and then you initialize a distributed optimizer, you broadcast this variable. So there are these number of steps. So the point is each of those steps is just one line, and you don't have to change your actual code by a lot, right? You don't have to rewrite everything from scratch. But if you want to go through each of these steps a little more in detail, we can do that in the next session. But just let me know that you want a detailed overview of Horrorwood, then we can do that. Last page, which was it? The Horrorwood part or the one that came after? The scaling part. Scaling part, that's okay. Like I said, it's slightly advanced and it's outside the scope of this course, but it's just something useful to know. So spend some time looking through this after the live session if you're interested, and then see if you understand it. If not, you can ask me, but today I think we won't spend more time on it because it's not really essential for this course. Okay, we will move on to the questions if not. Which TensorFlow distribute API is more suitable? The graph part. Yeah, I got that, but first I would have to kind of derive the speed up equation and then vary the number of processors and things like that to show you how you get the graph. So that will take another 10 minutes. So let's see, if I have time in the next week, I will maybe go through weak scaling and the graph. But it's not very essential for this course, so we'll skip it for today in the interest of covering questions that will help you with this course itself. Okay, we'll now start with the questions. So if you have an answer, please ping on chat. Which TensorFlow distribute API is more suitable for scaling up model to multiple nodes? Mirrored, parameter server, one device, central storage. Parameter server, okay. Anyone else? Yes, it is parameter server. As you saw from the definition, mirrored was just on one this thing, and parameter server is kind of intended for this as compared to the one device and the central storage. Yeah, so for people who don't remember, these two slides have the definition. So parameter server is a good option compared to all the others. Let's move to the next question. Throughput is bus width into latency divided by latency bus width divided by 8 into latency, none of the above. We have an answer saying B. Okay, anyone else? B. Okay. Yes, it is bus width by latency. Again, I don't have an explicit recap because we had it in the earlier slides, this part. So think about it. If you don't understand why, then we can talk about how that comes. Can I repeat first question? Yes. Which TensorFlow distributed API is more suitable for scaling up model to multiple nodes? Your options were mirrored strategy, parameter server strategy, one device strategy, and central storage strategy, right? So mirrored is kind of eliminated because it is on a single machine or a single node. Central and one device strategy are probably valid options because you kind of place it on the CPU, or here you place it on a certain device. But parameter server is typically the preferred way because again, because of the way it works, right? You have this server worker configuration, and the variables are created on the parameter server, and they are read and updated by workers in every step. So because of the way this is designed, this scales really well. So if you are asked about uh, scaling up on multiple nodes, then this is eliminated. These two are valid options, but they are not really preferred in this scenario because again, they are synchronous training methods typically, and they limit, because of that, they limit how fast things can go, right? Parameter server can be used, like I said earlier, it can be used for asynchronous and synchronous, but in the context of what we've discussed so far, in the TensorFlow context, I think it is used only for asynchronous. So it helps you scale up better, and that's why it's more suitable. Is this clear now? Okay. So let's, which of the following is which is true about model parallelism? Easy to implement. All workers train on different data. Gradients are exchanged during training. Activations are passed between GPUs. A, B, C is for data parallelism. Okay. D. Okay. Anyone else? Think about what you know about data parallelism and model parallelism. That will give you an idea of what the answer should be. For instance, what is exchange? How is it partitioned? Is it based on data? Is it based on the model? And things like that. I'll wait for a few more seconds and then we'll look at the answer. Can you repeat the question? Just what is true about model parallelism? I'm just waiting for more people to see if they have answers. Yeah. So let's look at the answer. It is activations are passed between GPUs. So again, like someone pointed out, data parallelism is easy to implement, and there the model is same across all the workers. You just partition the data between different workers, and again gradients are exchanged. And in model parallelism, you have to, assuming you are partitioning it layer wise from one layer to the next, assuming these are on different GPUs, you have to pass the activations. So that is true about model parallelism. All of these are for data parallelism. So if you find yourself being very confused by the definitions of data and parallelism, data and model parallelism, remember that if you're talking about data parallelism, data is what is replicated, what is partitioned. If you're talking about model parallelism, model is what is partitioned. That's all, right? So you might get confused when you think of data parallelism and then you think that okay, model is replicated. So why is it data parallel? It's data parallel because the data is what is distributed. Whereas in model parallelism, it's the model that's distributed. Once you think of this, you will be able to come up with these on your own, just reasoning about what the two things are. Is this clear now? Great. Let's move to the next question. Scaling issues occur in asynchronous communication, synchronous, both, none of the above. B, synchronous. Okay. Anyone else? B, okay. Let's look at the answer. Synchronous, yes. So why is this, right? Why can't you scale? So basically, you're in your synchronous thing. If you remember the definition which we saw somewhere here, right? We saw here. So in a synchronous training, basically the workers train over different slices of input data and then aggregate gradients at each step. So now that causes a bottleneck in a sense, right? Let's think about why. So if you had, let's say, two GPUs and both of these were doing, let's say, synchronous training, and they have to exchange gradients, right? So that causes, so basically till that exchange happens, neither of them can proceed forward. So this is what we call a bottleneck, basically. That's, I think that's the question that was asked. So there is this communication step that has to happen before either of them can proceed, and that's why it's called synchronous, right? Whereas in asynchronous, the parameter server, in that method that you learned, the parameter server handles this part. So this GPU1, the moment it finishes its computation, it can just send the gradients to the parameter server and continue working, right? There is no synchronization bottleneck, there is no communication bottleneck happening there. Whereas here you have this wait and exchange thing, and as you increase the number of GPUs, which is what scaling refers to, you can't scale very well, as in you can't get good performance, basically because of this exchanging gradients, right? This causes all of them to wait for each other, and till this communication step finishes, they can't proceed, right? So that's why in synchronous you have a scaling issue, whereas asynchronous, it scales reasonably well because each worker can kind of go ahead. Weak scaling can explain this question. Yes, you can think of it in those terms. Any other doubts on this? Bottleneck means what? So, again, maybe a very simple analogy is to think of a bottle, right? Then the etymology of the word, where bottleneck comes from. So, think of a bottle. Typically, a bottle has a very narrow neck. So, even if you have a wide bottle, the neck of the bottle is narrow. So, what happens is, if let's say I had a vessel with a wider brim, right, then the volume of water that comes out through this opening is a lot more. But now, because of the way the bottle is and because of the way the neck of the bottle is, it puts a limit on the volume of water that I can get out in a unit time, right? That's the idea of bottleneck. So whenever we talk about systems and we talk about, let's say, communication, in this context we're talking about communication, it could also be about computation, it could be about fetching data. All of these things could act as a bottleneck. Basically, if you have multiple steps in a pipeline or in a workflow, and if one of them acts as the limiting factor, think of the neck of the bottle, right? It acts as a limiting factor. So if one of them acts as that limiting factor, then we talk of that as a bottleneck. So this could not only be for communication, it could be for computation, it could be for IO, it could be for anything. Is that clearer now? Okay, good. Command to display GPU direct communication matrix for the system is, okay, we have one answer saying A. Anyone else? A, okay. Yes, A is the right answer, as we saw earlier, topo -m. You can look, if you're interested, you can look at this command's man page or its manual page basically to see if these are valid options and what they do. Yeah, that's what I'm about to suggest as homework, so you can go look that up. Let's move to the next question. Which of the following is a distributed deep learning framework? And you have 4 options. D, Horwood. Okay. Anyone else? Easy to use. Okay. D. Okay. D. Yes, the answer is D. And a good practice that I recommend throughout this course is, when you don't know what some of the options mean, go look them up. For instance, this that I told you, right? These could always be a variant of the same question. So you should always try to look up the options that you don't know. For instance, you know what Horwood is here, you know what NCCL is here. These have not been covered as part of the course. For instance, DALI is a data loading library that NVIDIA gives you. So instead of using the PyTorch data loader or the TensorFlow's data loading library, you could use DALI, right? So whenever you do see some unfamiliar options, a smart thing to do is to always look them up, so that if you have a variant of a question that asks you about one of them, you'll be able to answer them, and you'll also be able to eliminate out options because you're kind of familiar with what the others are. So do that for this question also. Look up what NeMo is. Hope this is clear. Hope why Horwood is the answer is clear. Okay, let's move to the next question. Which is the topology aware communication centric NVIDIA library? You have 4 options. Okay, C, NCCL. Let's look at the answer. It is NCCL. Again, go look up all these others and at least, if, out of curiosity, understand what they do. But yeah, as we already saw, topology aware communication centric library is NCCL. NCCL is used for communication matrix. Yes, it's basically, it is aware of topology and it implements a lot of communication primitives based with that awareness. Which of the following is /R true about Horowitz? You have three options and combinations of these. Take your time to look through it. One and two, which is A, all of the above. D, okay. D, yeah. So it is all of the above. So if you don't remember, um, yeah, easy to install and use, minimal code changes, uses advanced algorithms from HPC. So you'll see a lot of tools and frameworks borrowing from the HPC side of things, right? Because that's again another place where communication mattered a lot. So there have been algorithms and libraries like MPI that are there in the HPC world, and some of these try to build on top of those and use existing things from those. So the right answer here is D, all of the above. Okay, next question. NCCL uses automatic topology detection to scale HPC and deep learning applications over PCIe and NVLink. True or false? I think it's a very easy one. Answers? True, true, true. Okay. Yes, it is true. Like we spoke about, it detects the topology automatically and uses that to scale deep learning applications. And NCCL is not only used for deep learning but also HPC. So the answer is true. Let's move to the last question. Command to run Horowitz on 4 machines with 4 GPUs each is, and you have 4 options. C, okay. C, C, okay, everyone thinks it's C. It is C, right? And if you remember the details about Horowitz, it spins a process to one GPU and then it uses a separate process, right? So here you have 4 machines with 4 GPUs each. So overall you would need number of processes 16, and on each of these machines you're asking it to use all 4 GPUs. That's, I think, broadly the syntax, but you can confirm it. I just looked at the example you had in the slide, but please check Horowood's official documentation on this also. Yeah, the pin each GPU to a single process is where 16 comes from. Okay, I think we're already a couple of minutes over 9, so we'll wrap up here. If you have any questions or doubts or something that you would like me to address in the next class, please drop a note on chat. I'll stay on the call for a minute more. If not, thank you so much for joining and keeping it interactive, and I'll see you guys next week. Revise week 6 assignment, yes, we'll definitely do that in the next session. I also need to open it up and look at what the answers are and what the questions are. Now, unfortunately not possible. I'll need to take a look at it before. In case you have doubts like that ahead of the live session, you can post it on the discussion group or even on the YouTube channel as a comment, and then if I see it in time, I'll definitely address it. But I need a little bit of an advance notice. I also have meetings after this, so I can't stretch too much beyond this. Repeat 8 and 6. Let me see if I can quickly do that. So the 8 is about Horrorwood. So again, we talk about Horrorwood here in our recap. So again, like a lot of tools, it is easy to install and use. It has minimal code changes, uses advanced algorithms from HPC. So you can look at the example in the course slide that you have on what you need to do to use Horrorwood, right? So that will help you understand how it is easy to use, how it has minimal code changes. This uses advanced algorithms from HPC. You might not be able to directly connect with, but you can take a look at the Horrorwood website and understand a little bit more about what it does, right? That will help you understand the last part. Then, so that's question 8. Question 6, which is a distributed deep learning framework? Again, it is Horrorwood, because NCCL, as we see in the next question, is a topology aware communication centric library. So it helps you scale up deep learning training, keeping in mind the topology. It's topology aware, right? Whereas Horrorwood is a distributed deep learning training framework. That's different. DALI, as I said, is a data loading library. Again, something that is not discussed in this course, but it's good to have a one-line understanding of it. And similarly, you can look up what NEMO is. I'm not familiar with it, but feel free to look it up after the live session. Can I take live session every day? No. As per NPTEL's current guidelines, it is set to be 2 hours every week. So earlier it used to be 1 hour per week, and now they've kind of expanded it to 2 hours per week. So if you feel that you would benefit from more than one live session, please feel free to put that as part of the feedback. So there are a lot of complicated logistics on my side as well as to how these hours are counted and things like that. So I can stretch by more than 5-10 minutes per session, but it's not possible for me to take live sessions every day or 2 live sessions per week unless the regulations change from NPTEL's side. So if you feel that's something that would help you, please give that as feedback. Okay, if there are no other questions, thank you so much for joining, and look forward to seeing you guys next week as well, and hope you learned something from this session. Thank you. Glad to hear that. Thank you. See you next week. Feel free to drop off if you have more questions. Thank you. Thank you.